So let us continue with the methods of preparation of ethers. This time we would start with from alkyl halides. Now we have already seen the first two methods, that is by dehydration of alcohols and also from alcohols and diazomethane. This time we would begin with from alkyl halides. Now this can be done in two ways. The first way is by using dry Ag2O, that is dry silver oxide. The next method is by using Williamson's ether synthesis. So let us begin with the use of dry Ag2O for the preparation of ethers from alkyl halides. Let us take an RX, which is an alkyl halide. To this let us add Ag2O. Now what happens here is the ratio of Rx to Ag2O is 2:1. So we add one more molecule of Rx. And when we heat this, what happens is that Ag reacts with X to form AgX. And what we are left behind with is ROR, that is an ether. One very important point that one must notice here is that if at all we use moist Ag2O, if at all water creeps into the system, we would get an altogether different product, which we have already seen. So let us recollect the same. We know that moist Ag2O reacts to give AgOH. Now in this AgOH, Ag reacts with X to give out AgX, and the obtained product is an alcohol and not ether. So while preparing ethers, we must make sure that there is no water in the system and the system is completely dry. The next method, as we discussed, is Williamson's ether synthesis. In this, what happens is that we take sodium alkoxide, that is RONA, and to that we add an alkyl halide under alcoholic conditions. What happens is that there is loss of an NaX molecule, and the things that we are left behind with is ROR dash, that is an ether. Now one very important point that you must notice is that RONA is unstable and it cannot be stored in bottles. Hence it is prepared in situ, that is it is prepared while the reaction takes place. And how is it prepared? It is prepared by taking an alcohol, and when an alcohol is treated with sodium metal, it results in the formation of sodium alkoxide with the liberation of H2 gas. So this is how an sodium alkoxide is produced. Now for example's sake, let us take sodium methoxide, that is CH3ONA, and to this let us add ICH3, that is iodomethane. Now this iodomethane, when heated under alcoholic conditions, lose NaI molecule, that is sodium iodide, and what we are left behind with is CH3OCH3, which is dimethyl ether. Another example that we can take is sodium ethoxide, which is C2H5ONA, and to this we would add ICH3, that is iodomethane, under alcoholic conditions and heat them. Now what happens here is again there is loss of NaI, that is sodium iodide, and what the product that we get is C2H5OCH3, which is ethyl methyl ether. Now moving ahead, we can also use this method for preparation of aromatic ethers. For example, let us take phenol. To phenol let us add NaOH. This results in the formation of sodium phenoxide. This we have seen numerous times already. Now to this sodium phenoxide, let us add CH3I under alcoholic conditions and heat them together. Now Na would react with I to produce NaI, and the product that we are left behind with is a benzene ring with an OCH3 called as anisone or methyl phenyl ether. So Williamson synthesis can be used for the preparation of alkyl as well as aryl ethers. Now moving ahead, let us have a look at its limitations. Now if we take a tertiary butyl bromide, which is a tertiary example, to that when we add C2H5ONA, that is sodium ethoxide, and when we heat them under alcoholic conditions, instead of undergoing substitution reaction, this system undergoes elimination reaction to give us isobutylene NaBr and C2H5OH. But we had expected the product to be an ether, we got an alkene. So we must keep this in mind that only a primary alkyl halide can give Williamson's synthesis. Otherwise, if we use a 2-degree or a 3-degree alkyl halide, we would get an alkene. So now if I ask you a question, how will you prepare methyl isopropyl ether by using Williamson's synthesis? You may tell me that, so we can use isopropyl chloride, and to that we can add sodium methoxide, okay, and this would give us the the required product, that is methyl isopropyl ether, and the byproduct that we would get is NaCl. But this answer is completely wrong, because we have just learned that the alkyl halide used in Williamson's synthesis has to be a primary alkyl halide and not secondary or tertiary, because 2 degree and 3 degree alkyl halides give alkenes by elimination reaction instead of undergoing substitution reaction. So we must take a primary alkyl halide, that is we would take methyl iodide, and along with that we would take NaOCH3CH3, that is sodium isopropoxide, and when these react under alcoholic condition we have loss of NaCl, and the product that we get is the required one, that is methyl isopropyl ether, also known as 2-methoxypropane. So this was about the methods of preparation of ethers from alkyl halides.